Okay, this is a quick relative motion collision example problem. So I'm going to do an example here. If you've never heard of relative motion or done relative motion calculations, this video is going to be pretty perplexing. But if you have a little experience with relative velocity, then hopefully this will be enlightening. Okay, so this is the problem we're going to attack. This is a problem about a drone that moves east, meaning in the positive direction, and I give the speed relative to the Earth above the horizontal. It shoots a package at a speed v relative to the drone, and then the package is meant to land on a helicopter that's moving west, that's in the negative direction, and the helicopter apparently is accelerating upward relative to Earth. It also says the helicopter is h meters below the drone, and what they want to know is how far east of the drone should the helicopter be when the drone shoots the package. This word salad is basically unsolvable as written. One of the problems with it is that the information is given in multiple reference frames. Let's actually collect all the information that's given in the problem. They give us the speed of the drone relative to the Earth. That's here. They give us the speed of the package relative to the drone. That's here. That's here. So the ballistic package, okay, and that's relative to the drone. They give us the velocity of the helicopter relative to the Earth. So they give us the velocity of the helicopter and the acceleration of the helicopter, and that's upward relative to the Earth. I guess I didn't write A, so I'll write A here. I put it in later. So this is 0, comma, AH, they say upward, right? And then the other thing they do, this is really weird, they give us the position of the helicopter relative to the drone. So they give us the position of the helicopter relative to the drone. So the first thing we need to do is pick a frame. You cannot do this problem until you pick one frame. And my advice is you have two things that are going to collide. The package collides with the helicopter. Pick either the helicopter's frame or the package's frame. The reason I say to do that is if you pick that frame, then you only have one object to track and you're simply waiting for that object to return to the origin. In other words, if you're in the helicopter's frame, it's always in the origin. If something crashes into the helicopter, you simply need to find the time when that thing returns to the origin. So that's our plan. We're going to do it in the helicopter's frame. So I need the position of the package relative to the helicopter, and our rules for relative velocity are if I want P the package relative to the helicopter, I need two things on the right side, and the first index I write should be a P, and the last index I write should be an H. The index that goes between, in this case D, has to be the same index, and it doesn't matter what index it is. I could have put the Earth there, for example. The reason I put drone here is because I already have a VPD. The problem gave it to me. I don't have VDH, although I don't have XDH, although I do have XHD. And so perhaps you remember that XHD is equal to minus XDH. If I say that you are to the negative of me, then you would say that I am to the positive of you. Or if you're to my left, then I'm to your right, is another way to say that. Okay, so that's the position. I can plug these things in. The position of the package relative to the drone, at least at the start, is 0. They are in the same place. The helicopter is h meters below and d meters to the right. We don't know d. That's actually how far east. That's what we're trying to solve. And so I put a minus sign on this because I want dh instead of hd. Okay, so that's that piece of it. Now let's find the velocity. So the velocity of the package relative to the helicopter, that's the velocity of the package relative to the drone relative to the helicopter. Now I have the velocity of the package relative to the drone. This piece is fine. This piece I don't have, which is rather annoying, although I just used the same rule I used before. So I like this for an example problem because it lets us use this rule again. So check this out. I have a D first and an H second. So I put my D first and my H last, and sandwiched between the two, I have the same thing. In this case, the Earth. And the reason why I put the Earth between them is because I'm given VDE in the problem. So you see, you don't always have to put the same thing in between. You just kind of look at what you're given and you say, well, what can I do with that? So long as you follow these index rules, in other words, always sandwich the thing you want to get rid of in the middle, you can use whichever one you want. So I'm given the velocity of the package. Okay, so the velocity of the package, that's given, and I have some angle here and some angle here. And then I have the velocity of the drone with respect to the Earth. That's given in the problem. And then I have the velocity of the helicopter, which is uh, given in the problem. Now, one thing to note again is I have VEH, so that's the negative of VHE. In other words, it becomes positive again. One thing that's maybe a little confusing is maybe these angles. Bear in mind, I tried to make the problem simple by talking about the angle relative to the horizontal the whole time. These vector addition rules look like this. You're taking the velocity of one thing relative to another, and you are adding another velocity vector to it. So this might be v23, for example. And the way you add velocity vectors is you add the x components to the x components. And in order to have x components that are consistent, you always want to have the same x-axis. So I did it to the horizontal in both cases. If I wanted to be fancier, I could have given the angle relative to the drone. And then, okay, you've got a little bit of angle arithmetic to do, maybe theta 2 minus theta 1. Let's not worry about that for now. There's enough juggling to do in this problem. I'll just say that the angles I give are the angles you want to use. Okay. By the way, I'm going to do a numerical example after this, so we'll get to go through the whole thing again if the notation bothers you. It's going to get a bit messy when I do quadratic formula later. Anyway, let's keep going. I need the acceleration of the package relative to the helicopter. So same rule as before. I just put minus signs on things where the indexes are reversed. Okay, and so now I finally have a collection of vectors that I can do some kinematics with. These are all in the same frame, okay? And now what I'm doing is I'm only tracking one object. That's the package. So I have the final position of the package equals the initial position of the package plus v initial t plus 1/2 at squared. We are back in plain old 1D kinematics land. The relative velocity part of this problem is over. What I do now is I plug in all the stuff that I had before. And okay, I admit it's a little messy. You'll see when you get numbers in a problem like this, this looks very simple. But I wanted to keep it general. I want you to see how this goes. Okay, so this looks like one equation, but it is actually two equations. It's one equation that talks about x components, and it's another equation that talks about y components. I can write those two equations right below. So now I have two equations and two unknowns. Okay, so let's get rid of all this mess and just go back up here. These are my two equations, okay? We can solve this equation for t using quadratic formula. And if you're like, oh my God, that looks like it's going to be really messy, you're absolutely right. It's horrible. But once I put numbers in, it looks a lot nicer. Again, I just want to keep it general. We'll put numbers in in 2 seconds, we'll put numbers in. Okay, so that's the time. What I do is I take this value of time and I punch it in here, and boom, that is the general distance formula. If you want to go write a simulation which has things crashing into each other, this is the formula you would use. If you are just trying to solve a problem for a quiz or an exam, then you'll get something that looks like this. So you've got a drone, it's moving east, 20 meters per second relative to the Earth at 30 degrees above the horizontal. It shoots a ballistic package at 30 meters per second relative to the drone at an angle of 50 degrees. The package is meant to land on the helicopter moving west. The acceleration is 5, and the helicopter is 100 meters. So I took the same problem and I just put some numbers in, and I want to show you it all over again. Okay, so what are we given? We're given the velocity of the drone relative to the Earth. We're given the velocity of the package relative to the drone, the velocity of the helicopter. We're given the position of the helicopter relative to the drone. And here I was a good boy and I put in acceleration of the helicopter relative to the Earth. I'll do a little bit of calculator work here for you. This is what my actual vectors look like. And now I proceed to my kinematics. So here are my kinematics. I don't know what happened to that thing. Hopefully it comes back. These are my relative positions I need to find. Okay, so okay, there it is. It came back. So here's my positions I need to find. Okay, so the position of the package relative to the drone is 0, 0. In this case, the drone is D to the left and H above the helicopter. Okay, so that's that. The next piece is the velocity. So I'm just going to plug in all the stuff that I had above. This is the exact same thing I had last time. I'm just showing you what it looks like to plug the vectors in, and I just end up with some number, okay? Some vector anyway. And then I do the same thing with the acceleration I did before. So the acceleration of the package relative to the helicopter is the package relative to the Earth plus the Earth relative to the helicopter. If I punch that in, I get this, and then I write my kinematics formula. And now when you punch in for the kinematics formula, this is actually pretty easy. You've got two equations, two unknowns. Okay, so let's separate them. Two equations, two unknowns. This looks a lot nicer than the crazy thing we were looking at earlier. For this one, you can punch it into a quadratic formula calculator or do it by hand if you're hardcore. I've done enough algebra for today, so I'm going to cheat. And I'm going to use a quadratic formula calculator. I get 6.4 seconds. If I take that 6.4 seconds and I plug it in here, I get 394 meters. So to be clear, I found the time when the package goes to the origin. And if that sounds weird, you're like, that's really weird. The package isn't going to the origin. How do I know that this is real? How do I know this is real? Well, okay, here's some dessert. I'm going to simulate the whole thing on Desmos for you. What I've done is I've put everything in according to the Earth. So these look a little different than what I had before because this is all in the Earth frame. I've got 3 items that I'm going to track the motion of. The purple is going to be the plane. The green is going to be the helicopter, and the red is going to be the package. And I'm going to play a little movie for you, and you get to watch what happens according to the frame of the Earth. Now, the plane, remember, should just continue in a straight line motion up this way. The helicopter should accelerate upward because that's what it said. And the package should start moving upward but then fall because it's ballistic. So let's see if all of that happens. You know what that's called, friends? That's called Miller time. All right. Hopefully this video was more helpful than confusing.